Hi class, so we meet again. In this video, I'm going to show you on how to solve your gas power cycle when you have a dual cycle here, where you have heat addition at constant volume and heat addition at constant pressure. So let's read the question first. It says that an ideal air standard dual cycle has a compression ratio of 17:1 and a cut-off ratio of 1.1. At the beginning of the compression process, the air temperature is 30 degrees C at a pressure of 110 kilopascal respectively. The pressure is double during the heat addition process at constant volume. If the mass of the air is 0.5 kilos, sketch the cycle on a PV diagram, and you need to determine the heat addition at constant volume and also at constant pressure, the network of the cycle, which is Q in minus your Q out, and the thermal efficiency. So let us sketch the PV diagram first. So since this is a dual cycle, so you are going to have one heat addition at constant volume, and this is heat addition at constant pressure, and you are going to have heat rejection at constant volume. So let's connect this thing together. So let's label this as 1, this is going to be 2, this is 3, this is 4, and finally you have 5. So as you see here, from state 2 to 3, this is your heat addition at constant volume because you have V2 is equal to V3 here. And then you have another one, which is heat addition at constant pressure between 3 and 4. So let's label this as your Q in first so that you are not going to forget. This is going to be your Q out. And it gives you a cut-off ratio. Means that denoted as VC, which is your V maximum over V minimum. So as you can see here, your V maximum is right here, and V minimum U is this one, your V2. To have a better view, if I were to sketch a piston cylinder here, so when you have a compression, what will happen to your piston is it will end up in here. So this will give you volume at 1, and this is volume at 2, and it is equal to your volume 3. And let's get back to this compression ratio here. So V1 over V2 given to you as 17. And then you have a cut-off ratio of beta, which is beta is actually V4 over your V3, which is equal to, in this case, 1.1. Now, what is cut-off ratio? Cut-off ratio is the measure of volume in between after complete combustion and just the volume just before the combustion is about to begin. So in this case, it is denoted as state 4 and 3. That's why it is V4 over your V3. And it also gives you mass is equal to 0.5 kilos. And the temperature at the beginning, which is T1, is equal to 30 degrees C, and you need to convert it into Kelvin, so it's becoming, you need to plus with 273, so it becomes 303 Kelvin. And the pressure at the beginning of the compression is 110 kilopascal. Right, now that we have all that we need, so let's have a look at what the questions want. So question 1 asks you to find the heat addition at constant volume and heat addition at constant pressure. So you have one heat addition at constant volume, which is Cv times with your temperature at 3 and temperature at 2, and Q34 is between constant pressure over here, Ct temperature at 4 and your temperature at 3. Next you need to find the network of the cycle, which is network can be found from Q in minus Q out, and because you have two process of heat addition, so it's going to be summation over here, and your heat rejection is in the exhaust process, which is in between 5 and 1. And finally you need to find your thermocycle efficiency, where you have this equation. So you just plug in what you have obtained in Q in and this Q out. So let us solve it from process by process. So state 1 to state 2 is isentropic compression process. Since this is an isentropic compression process, so you can use this isentropic equation or relations. Bear in mind that we are going to find this temperature at 2 in order for you to solve for your heat addition at constant volume. Alright, so since we are looking for the temperature at 2, we can make use of relation between temperature and volume, because you have this volume ratio, or indicate as compression ratio, which is RC. I have this one I have corrected, this one is RC, not VC. So what you have is, so you plug in all the value that you have, which is T1 is 303 Kelvin, and your compression ratio is 17. K here is actually your gamma for your air, which is 1.4. So 1.4 minus with 1, you got 0.4 over here. So you will get 941.07 Kelvin for the temperature at 2. And we are going to make use of the same relation to find your pressure at 2, but right now you are going to use this between pressure and your volume. Alright, with the same isentropic relation between pressure and volume, we now need to find the P2. So what's happened here is that your V1, V2 is actually your RC, so bring this thing to the right hand side, so you are going to left with K, and you plug in all the numbers, and finally you will get this value over here. And please bear that it says here the pressure is double during the heat addition process at constant volume. So this is the heat addition at constant volume, and the pressure is double during this process, meaning that your P3 is actually 2 times of your P2, which is equal to 11,615.85 kilopascal. Now we have done this isentropic compression from 1 to 2. Let's move to the next process, which is constant volume heat addition at 2 to 3. So we make use this PV is equal to MRT equations, and then because volume at 3 is equal to volume at 2, so you equate it V3 with V2, and then you make use of that PV MRT. And because we are talking about closed system, so the mass is constant, and we are analyzing of the same air, so your R is constant. So you can cancel out these two terms and left with you with this equation here. So we have already find for your P2 and T2, and also P3 is 2 times of your P2, and when you plug in all the value, you are going to have this temperature. And if you wanted to check, you will see that your T3 value must be higher than your temperature at 2. So now that we already have state 2 and 3, next is to move to this relation, which is heat addition at constant pressure, so that we can get the temperature at 4 over here. So we have heat addition at constant pressure. So we equate P4 is equal to P3 and make use of this PVMRT, and we arrange it here. So again, mass and R is the same value, so we can cancel out. So left with you this T4 is equal to V4 over V3 times with your temperature at 3. And if you have a look at your V4 over V3, it is actually your cut-off ratio over here. So you substitute the value into here. T3 is already, we already find T3 previously, so you just times with these two and you got T4 is equal to 2070.35 Kelvin. And now finally we have the relationship between 4 and 5, so that we can find the temperature at 5 in order to solve for your Q out over here. So this relation is isentropic expansion in between 4 and 5. So we make use of this isentropic relation in order to find T and also your pressure over here. Alright, so let's have a look at this volume ratio first. You have V4 over V5, and V5 is actually equal to your V1 over here. So that's why you have V4 over V1 here. And then, in order for you to get your V4, it can be obtained from this V4 over V3. And to get your V1, it is actually can be obtained from this relation of your RC. But your RC is V1 over V2. Now you inverse it, so it's become V2 over V1. And in order to get your V4 over V1, so what you need to do is that you need to cancel out the term of your V3 with V3, and another one is V2 with V2. So that left with you only V4 and V1. Then only it will be equivalent with this one and here. So please note that your V3 and your V2 is equal. So it is actually 1. And then your V2 and V1 is actually inverse, so it is 1 over RC. And that your V4 over V3 is actually your beta. Therefore, when you solve for this, you will get your V4 over V5. So you can make use of this V4 over V5 into here. So make use of the isentropic relations and the ratio of V5 and V4 that you get, and plug into the equation, so you have your T5 692.48 Kelvin. Now that we have all the temperature that we need, so we can solve all this problem. So let's list down from temperature 1 until temperature 5 that we have. So you can see that T4 have the highest temperature here. Means that if you have a look at this PV diagram, T4 is here, where the complete combustion process happen. So there's no more fuel and air to be burned. That's why you have the highest temperature over here. So now that we have all the temperatures, so we just plug in into these equations, and solve all the problems here. So once you plug in all the value in here, so this is the final answers that you will get. Please bear in mind that the CV that we are going to use is this value, and the CP is this one, and your R is this value. CV is going to be used in this constant volume heat addition and constant volume heat rejection. And you have another one, heat addition at constant pressure, which you are going to use your CP value here. Now you can try to solve it on your own, and if there's any changes or any mistake regarding on the final answers, please leave a comment in the comment section. Thank you.